Okay, so today you'll be sad to hear is our last lecture on algae growth modeling. And we're going to focus on the harvest. But first we have to clean up something in the nutrient code. Then we will first find the growth coefficient without harvest, just as we had the analytic solution without harvest for the logistic model. And then we'll find the harvest rate based on the growth coefficient. And then we'll try various harvesting methodologies. But one of them is we'll try harvesting at peak concentration, which would be at 6 p.m. just before dark. Okay, so the error in the code is that the concentration of the nutrients can go right past zero into the negative range. And so we have this example here with carbon dioxide where it's going below zero. And there's no such thing as negative nutrient concentration. And so, I mean, if the code was perfect, it wouldn't have negative nutrient concentration, but no code is perfect. It's an approximation of reality. So the nutrients drop below zero, so we're going to have to deal with that. So here's a closer look. And you can see that an excessive drop is triggered and becomes worse at the point where the nutrients concentration approaches zero. So you can see that here's zero, and then it drops into the negative range rather than just staying positive with a low value. So somehow carbon dioxide near zero triggered more rapid cell growth, which also resulted in more simulated carbon dioxide removal from the algae culture. So this type of error is very typical in coding, where you really didn't do anything wrong. It's just that there's a numerical error inherent in the algorithm. So we're going to have to add in some code that prevents nutrients from dropping below zero. So one thing I could do is I could just put in some if statements that say if the nutrient concentration drops below zero, then the nutrients are set at a low value. So what I'd like you to do now is add this into your code. Okay, so as you saw in your code, if you just prevent the concentration from going below zero, you solve that problem. But that's really not very realistic to keep the concentration at that value. But if you do put the concentration at that value, you can see that once the carbon dioxide gets to in the range of the half saturation rate coefficient, the concentration starts to go down because we don't build up as much concentration in the day. But really, if we're taking our carbon dioxide down to the range of the half saturation rate coefficient, we're artificially just keeping it there at that rate, right? So if we go to the next slide, you can see that if I drop it one more decimal point, that the concentration goes down even faster. And there's no growth during the day, basically, because my monod equation, the CO2 over the half saturation coefficient plus the CO2 concentration, is a very low value, like 0.01 or something, if I drop it by a decimal magnitude. So anyway, the growth rate or the decrease is even worse. Now, the question is, how much time should we spend on trying to simulate what happens when the concentration is close to zero? Any answers on that one? No time, because we don't want to operate an algae raceway with the concentration close to zero. We would not be achieving our goal of maximum biofuel production. So what we can do, instead of just setting it at a zero value, we can say, if our concentration gets close to the half saturation rate coefficient, and I said half saturation rate coefficient times 10, then we just add more CO2, okay? And the way we do that is we just say CO2 at I equals CO2 zero. So we just replenish our nutrient concentration. So you can see that I did that here. I just bumped my nutrient concentration back up. So that's a more realistic scenario. And that's what you would do in any kind of growth system. You would be monitoring when the nutrient concentration is getting low, and then you would add more in. And the closer you come to the optimal range, the better off you are. For example, out in the field agriculture, if we had way too much nutrients in the soil, what might happen? It could stress the plant. And also you could have a rainstorm or something, or big irrigation, you could leach the nutrients right into the groundwater. So it's very good to keep your nutrients right in the range that you want, especially with like controlled environment agriculture. You're going to keep your nutrients very close to the optimal amount. That's the reason you're doing controlled environment or hydroponics, is you're keeping your nutrients right at the amount you want. So anyway, this is what I'd like you to do, is when the concentration gets close to the half saturation rate coefficient, reset your nutrient concentrations back to the initial. Okay, now the next step is using our known growth rate, which we simulated here. Okay. I'd like you to output that to Excel and do it only for 20 days, not 40 days. Because if you try to simulate this end of the curve, your regression isn't going to be very good, because the logistic model won't fit that end maybe it will. But anyway, I did it for 20 days. So this is how you output the data. You make a pandas data frame, define some columns, and then you say that those field names, which are the column names, are equal to t, which was your time vector in NumPy, and your concentration vector. So you just so you first define the pandas data frame, then you add in the values. And then pandas has an Excel writer function where in this case I'm outputting it to my sample data file in Colab, and I'm making a new file called new file. And so I'm defining this writer. That's the location I'm going to send it to and the file name. And then I'm going to say output.toExcel, and it's going to output it to the writer, which is the location. And I'm going to give it the sheet name algae concentration. And it's very important that you write writer.close and then brackets. Otherwise, the Excel file won't work. Okay, and then your output data will be in a file like this, and it'll be in the sample data folder right here. And then you can just say download, and you can download it to your computer, and you'll get your time and your concentration. And then you know what to do with that. You set up a least squares analysis, where in column D, you'll put in the analytic solution to the logistic model. Notice that this is in the shape of the logistic model. And then you'll have your model concentration here. That's where this equation is coming from. And so initially, it's not going to be the same as column C, but you'll just put the equation in here, and then these are named cells, okay? So I've named the cells H1, H2, H3 as P0, K, and RR. R doesn't work because it means row in Excel, so you have to say RR. And B2 is the time, and so that's why I'm referring to B2 there. So I set up the equation for the model concentration, and then I use solver, and I put the sum of least squares here. So I minimize the sum of least squares, and I use the named cells as my objective function, or my objective cell is H5, where I'm trying to minimize that. And I'm doing that by changing these cells. And for this one, you do want to specify that it's in the positive range. You know, constrain your values to positive, because all these are positive. Okay, and then you'll get this, which you can see is a perfect match to the algae. And you can see why the logistic model is such a powerful model. It really does work. This one, it's because of light limitation. But, you know, there's all sorts of reasons for there to be an environmental carrying capacity limitation. In the case of algae, it's light. Okay. So then you're going to set your harvest rate, H, equal to that harvest R. And actually, when I said harvest R, I mean this R here, this RR that you get from minimizing the least squared errors. So here's the data that I input to the model, to the Excel file without harvest. And then just like you did in the harvest homework, you're going to add this term to your Euler equation. Okay. And notice that when we add harvest, our concentration is 0.9, in the range of 0.9 instead of 1.8. And that agrees with the theory. Remember, if we harvest at half of R, then our concentration is going to be half of the environmental carrying capacity. That's just how it works out. And so one other thing I'd like you to notice is when we didn't have harvest, we reached our maximum at about 15 days. And when we have harvest, we don't reach our maximum till about 30 days. So it delays the increase in concentration. Okay. Then once we get our harvest, we want to see what the harvest rate is and what the cum harvest is. So we add 2 more lines to the code where we calculate our harvest at each time step, our harvest rate. That's what this harvest is, which would be kilograms per day. And that's why I don't have to multiply times dt in this equation. I have H, my harvest rate, times my concentration, times my volume, the volume of my reactor. And in this case, we're going to have a more realistic scenario as far as the size of a commercial raceway. And this is actually a little big, probably. 1 hectare is 2 acres. 1 hectare is 10,000 square meters. And we're going to say that the depth is 10 centimeters. And so our volume is going to be 1,000 meters cubed. And so I've already showed you that if we have our concentration in grams per liter and our volume of our reactor in meters cubed, that they sort of cancel out, and I can just use this equation to calculate kilograms per day. So I have my kilograms per day, but I'm harvesting 24 times a day in the model. So then I'm not going to get kilograms per day at every time step, or kilograms, total kilograms, unless I multiply times the time step. So this is like dividing by 24, since dt is 0.041. And so you're going to have to set up some vectors in your model, you're going to have to add a harvest numpy array and a cum harvest numpy array. And you're going to have to make a new plot with harvest and cum harvest. And so you can see that my harvest is 6,000 kilograms. My cum harvest is 6,000 kilograms. And my harvest in kilograms per day is too low down here to see what it is. But what we're really interested in is how many kilograms we're getting off the raceway. And so we're getting about 6,000 kilograms off the raceway if we just harvest at a constant rate from the time we start. So if you're watching this on a video, what I'd like you to do is stop the video here and add in the numpy arrays that you need, the plot statements to produce the graph. Okay. So here are the arrays. And so we have our harvest array that we're adding in, np.zeros, our cum harvest array, np.zeros. And we're adding in these harvest statements, very simple. Just right after you calculate the concentration, just add in the harvest statement and the cum harvest statement. And then for our plot, we just have T versus harvest and T versus cum harvest. Okay. So if you're just watching this on video, what I'd like you to do now is delay the harvest until the concentration the concentration in the raceway reaches 0.6 grams per liter. Okay. So here's how we do that. We have, instead of just saying harvest equals H equals harvest R over 2, we're going to have an if then statement. We're going to say if C at I minus 1, the concentration here, is greater than 0.6, then H equals harvest R over 2, else H equals 0. Okay, so here I've done that. And now you can see that the concentration goes up very quickly. And then I start harvesting once it gets to 0.6. And you can see that now I'm getting almost 7,000 kilograms of harvest after my 40 days instead of 6,000. So I did get a lot more harvest out of the raceway by delaying the harvest till the concentration increased. Okay, now what I'd like you to do, if you're watching on video, is see if you can harvest once per day right here at 6 p.m. and see if you get more yield by just harvesting once per day. So what you'll do is you'll harvest 24 times the normal amount once per day instead of running it every harvesting all day long. Yeah, you're just restricting it to 1 hour. Okay, so try that. And here's the result. We get a step harvest, and we can see that our harvest is every 24 hours. And we can see that our concentration is kind of weird. I don't know exactly what's going on, but it looks like it's dropping. And then it's having the normal decline during the night, and then it's going up. So the way that we would do that is we would say, if C at I minus 1 is greater than 0.6, because we still want to delay until 0.6, and time of day is greater than 0.498 and less than 0.512. And the reason I said that is, remember we used that modulo and we had I minus 6? And I'm not absolutely sure about this, but I think that means that if our time of day is 0.5, then that would be 6 p.m. I haven't verified this, but I think that's what it means. And then notice my H is harvest R over 2 divided by DT. DT is 0.04167, which is like saying H equals harvest R over 2 times 24. So I'm harvesting 24 times the amount at that one time step. And then I printed out my cumulative harvest I think it's 6828. I'm a little confused here. But anyway, I'd like you to do this. Plot out your cumulative harvest at NT minus 2. That's 2 time steps before the end. And actually print out and see if you get more at 6 p.m. than at like noon or 11 p.m. So that's what I did here. If I harvested at 6 p.m., I got 7,013 kilograms. And it should say kilograms here instead of kilograms per day. But if I harvested at 11 p.m. after it had started decreasing, I got 6828 kilograms. So yeah, there is a relationship between time of harvest and so if you have extra time on your hands, you can investigate what time is the best time to harvest. Those are the kind of questions that people who are growing algae and algae race spend their time talking about. What time should we harvest? Should we harvest all the time or should we just harvest once per day? You know, those are the big issues out at the raceway. Okay, we'll see you next time.